Hi, welcome to Math Stat 341 Probability, lecture I think 9. Today we're going to do three things. We're going to do trump splits, conditional probability, and we're going to do a little bit of Bayes' rule, or Bayes' theorem. What I want to do again is rather than just immediately giving you some formulas, try to help you sniff out what should be the right answer. I also want to try to deliberately do some mistakes in the lecture today as opposed to the accidental mistakes that I have been doing so far this year. And the reason is I want you to get used to trying to see, is this reasonable? Can I trust this? So I want to talk about, building on the lecture we had on Monday, more things to do with the deck of cards. One of my favorite games is bridge. In previous years, I've actually run lunch groups to teach people how to play. We don't need to know too much. You have 4 players, 2 teams of 2, standard deck of 52 cards, so there are 4 suits: spades, hearts, diamonds, clubs. You have an extremely complicated bidding convention that you agree upon with your partner. And often one suit is declared the special suit and it is the trump suit. And that suit becomes more important than the others. So if you normally play, whoever plays the highest card wins that round where everybody plays 1 card. But if there's a trump suit and you are able to play a trump, the lowest trump beats the highest ace in any other suit. So we frequently care about how are the trump distributed among the 2 hands. If you and your partner have all the trump, you're in great shape. If you yourself have all the trump, you're in even better shape. No one can stop you. Because if all you have is trump, everyone, I trump this, I trump this, I trump this, I trump this. It's really nice. It's also extremely unlikely unless you cheat. And we'll talk about how to do that later. So you might want to calculate what's the probability of different trump splits. So because there are 4 people, everybody has 13 cards in their hand. So assume you and your partner have 8 trump. So there are 5 left for the other 2 people. And it's actually better, yes?
Sorry, how do you know if it's a trump card yet?
So there's a complicated bidding scheme. And at the end, whoever bids the most can declare what trump is. And in fact, in bridge, your declaration is forced upon you from the bidding. In an easy game, whist, you actually get to declare what you want trump to be.
It's like any kind of card, like any suit.
Right, so for us, we'll say maybe hearts are trump for this hand. And so we'll say hearts. And so there are now 5 hearts that are split between the other 2 hands. And we want to know how they split. It turns out the more evenly split they are, the better it is for you, because the more likely you can get each of your opponents to drop a trump card at the same time if you're playing out your top trump. The worst thing for you would be if one person has all. So the question is, what is the probability of a 5-0 split? And again, all of this stuff is motivation. I just want to know, between myself and my partner, we have 8 hearts. There are 5 hearts remaining. What is the probability that one person has 5 hearts and the other person has 0? So I'm going to show you 3 ways to do this. The first way, you have 2 choose one ways of choosing which person has the 5 hearts. Okay? Now, you have to give them all 5 hearts. 5 choose 5. And then how many cards do you need to fill out their hand?
8 more.
8 more. And how many cards are left available at this point in time? We had 26 cards. You and your partner have 13 each, that's 26.
19.
There's 21 cards. I'm sorry, there's 26 cards left over. You've already given 5 hearts to this person. So how many cards are still available to assign? 21. And of those 21 cards, how many must they get? 8. Now, if you want, you can write the next term, or if you want, you can ignore it. How many cards are left? 13. And you have to give the remaining person 13 cards. How many ways can you give 13 cards from 13 to the remaining person? One way. I can be really pedantic and write 13 choose 13. It's not bad to do that. So this is, choosing person. So give the 5 hearts. Fill to 13 cards, and that's the other person. And now, how many ways are there to take the 26 cards and make 2 hands of 13? Yes?
We just want to choose 13 of those.
Right.
So 26 choose.
And again, if you wanted to, you could be extremely pedantic and put the 13, choose 13. But once I choose 13 cards for one person, then the remaining 13 cards have to go to the other person. So this is one approach. Does this seem reasonable? And we can just calculate what it is. Approach 2. So again, we're going to start off with this 2 choose 1 ways of choosing which person is going to get the 5 hearts. What's the probability that the first heart goes to them? They've got 13 spots for cards, right? And I'm looking at a specific heart. What's the probability I give them that heart? I'm sorry? It's 50%. But I don't want to write 50% as 50%. I want to be extremely pedantic. I'm in a pedantic mood today. How should I write 1/2? They have 13 cards that I have to give them. There are 26 cards available. You said that the probability is 1/2. How should I write 1/2?
26 choose 13.
No.
13 over 26.
13 over 26, right? There's 13 slots, which could be a heart. And there are 26 cards. I have to put the first heart in one of 26 slots. 13 of the slots have the name person 1 on it. Now I go to the next heart. How many slots are remaining?
12.
12 in their hand and 25 total. What's the probability to get the next one? 12 out of 25. And then continuing the fun, 11 out of 24, 10 out of 23, 9 out of 22. And then do I need anything else at this point? I don't care where the remaining cards go, right? I don't care what slots. How many cards are left?
21.
Put them anywhere. And then we divide by 26 choose 13. We divide by 26 13? Yeah. Wait, no, I don't need to divide. I don't need to divide by 26 choose 13. That is a typo. That's a bad typo. Okay. And then here is one other way of doing it. I have 2 ways of choosing the person. Let's look at the cards one at a time. What's the probability that if I choose one of the hearts, it goes to the first person? And now we'll go back to how you originally phrased it. What's the probability that any heart goes to a person? 1/2. So I have 2 ways of choosing my person, and just 1/2 to the 5th. If you calculate what you get, the first one is approximately 3.913%. The second one is approximately 3.913%. They're actually the same fraction. And the last one is equal to 6.25%. We can immediately deduce that at least one of the 3 methods is wrong. It's possible that 2 are wrong, it's possible that all 3 are wrong. But we can't have all of them being correct, because the probabilities are different. What's the easiest way to determine which one is correct? Or at least to be confident about determining which one is correct?
Run a simulation.
You run a simulation. So simulate. So this is very similar to the king-queen problem I gave you. Have a deck of 52 cards, actually have a deck of 26 cards, and have 5 of the cards labeled 1, and have all the other cards labeled 0. choose 13 of them and see is the sum at least 5. Oh, sorry, see if the sum is exactly 5. Simulate this. Because 6.25 and 3.913 are so well separated, even 100,000 simulations, probably even 1,000 simulations, is enough for you to be extremely confident which one of these is wrong. You may not be confident that the other one is right, but you can at least eliminate one of these without too much trouble with simulations. So the issue here is that it's a conditional probability. That if I just specify one card, each card has a 50-50 chance of being in player one's hand. But once I start putting cards in player one's hand, it becomes less likely for additional cards. Imagine, if you only had fewer cards, slots in your hand, you would eventually have no chance of having more cards and be full. So for a lot of these, it depends on how you phrase things. Phrasing is extremely important. So I will mention probably one of the greatest groups of all time from the 70s. If there is time at the end of class, I will give you a cultural extra credit opportunity. The group is ABBA. So I don't know if I've shared any stories with ABBA. So let's imagine we want to have a partial reunion of ABBA, and we want to have 2 people from ABBA together. And we want each person to be equally likely to be chosen. That's not the same as every group is equally likely. So let's put labels, A1, B1, B2, A2. There are 6 groups, A1, B1, A1, B2, A1, A2, then we need B1, B2, B1, A2, and then B2, A2. So if you look at this, you have 6 groups. Everybody occurs in how many groups? 3. So everyone occurs in 3 groups. There are 6 groups, so everybody happens half the time. Now, the story of ABBA is sad. There were 2 marriages followed by 2 divorces. It is not unreasonable, based on the way these divorces happened, that you may not want to be reunited with your ex. So let's eliminate A1, B1, and let's eliminate B2, A2. How many groups are there now? 4. Is everybody still equally likely to be chosen? Yes. A1 occurs exactly twice. B2 occurs twice. A2 occurs twice. So when I say everyone is equally likely to be chosen, it is not the same as each subgroup is equally likely. The subgroup B1, B2 has a 25% chance of happening now versus around a 16% chance before. So I love the ABBA example as a way to illustrate just how important it is to talk about things. And then when we're talking about probabilities, are they independent or are they conditional? If I say, I'm forming a subgroup, okay, a subgroup of ABBA where you have divorces. I'm not going to have 2 X's together, and that is going to affect my probabilities. So what we want to do is we want to get a sense of how to adjust probabilities based on dependencies. So let's roll 2-pair die. And we'll assume the die is independent. What is the probability the sum is an 11? So how many ways can you roll an 11 with 2-pair die? Yes?
5 and 6, or 6 and 5.
So you have 2 ways to do it. And how many ways are there to roll 2-pair die?
36.
36. So it's going to be 2 out of 36. Or if you want to reduce, 1 out of 18. What is the probability the sum is a 3? Also 2 out of 36 equals 1 out of 18. All right, now assume first die is a, did I want to do a 6? Oh yeah. So let's do, instead of doing 3, let's do 7. So what's the probability we get a 7?
Oh, no, 6 out of
6 out of 36. Or 1/6. Now, let's assume the first die is a 3. And let's ask, what are the probabilities now? Probability sum is 11, given first is a 3. What's that probability going to be? Yeah, there is no way you're going to be able to roll an 8 with a standard die. The probability has changed. Not surprisingly, giving you the information that the first roll was a 3 affects your probability of getting an 11. What about probability the sum is 7, given the first is a 3? What is that probability?
1 out of 6.
Still 1 out of 6. So these are the same. So what we're seeing here is that there is no change in probability if I give you this extra information. This is essentially the notion of independence. Knowledge of one event does not help you with knowledge of another. Dependence, knowledge of one event helps you with knowledge of another. And so we always want to figure out, when do we have independent events, when do we have dependent events? These lead to what we'll call conditional probabilities. And so we'll introduce some notation, and then we'll try to figure out what is a good formula. So you have lots of different notations you can use. The standard one is to use a vertical bar. So conditional probability. So the probability of A slash B is the probability A happens given B happens. Right. When you're doing this, you often assume something about the probability of B. What might you assume about the probability of B? I'm sorry? It's not 0. Right? If the probability that B happens is 0, does it make sense to talk about the probability of A happening given that B happens? You might want to be able to discuss something like that because you may not know a priori that B doesn't happen. But the place where this is going to be the most useful is in situations where B happens. What is the probability of something happening given that Professor Miller is rooting for the Yankees? No, Professor Miller is not going to be rooting for the Yankees. It's not worth even trying to investigate this. All right? So let's think about what this means. I want to write the probability of A given B, and I want to try to write it as a function of the probability of A and the probability of B. How many of you actually know the formula for the conditional probability of A given B? Okay, we're going to see that this does not work. That you can't write this probability as a function of the probability of A and the probability of B. We'll need more information. And again, the reason I want to do this is the older you get as an educator, the less excited you get about teaching more and more content. And the more excited you get about just focusing on a few small things that your students can take away from the class. How can you sniff out an equation? How can you sniff out a reasonable relationship? What I want to do is imagine there is such a formula. Let's try to find it. So let's look at some special cases for A and B. So what do you think might be a really nice relationship between A and B? I want some relationship between A and B. What do you think would be really nice?
If they're independent, or
Okay, well we don't really know what independence is yet.
Or like disjoint.
Okay, so one is that they're disjoint. What else could they be?
complement.
Okay, so complement would actually be a special case of disjoint. So we could do A equals B complement. So that would be disjoint. In fact, the most disjoint possible, that they take up everything together. What is another relationship we could have between A and B?
It could be the same.
They could be the same. So you could have extreme sports, this is extreme probability. Right? You look at the extreme cases and you try to understand those. Now we have a lot of freedom in choosing A and B. What would you like the probability of A to be? You get to choose a number between 0 and 1. What might be a really nice number to choose? We're trying to show that this can't work. What would be a good number to choose? 1/2. Because if we choose 1/2 for A, then that's 1/2 for B. So choose probability A equals probability of B equals 1/2. And let's still have over here the probability of A equals the probability of B equals 1/2. Now in this case, what is the probability of A given B? This is the probability of B complement happening given that B happens. What's that probability? 0. In this case, it's the probability of A given B, so it's the probability of A given A. What is the probability of A given A? 1. And these would both be f of 1/2, 1/2. If there was a formula like this, then we have this absurdity. So this tells us that conditional probability has to depend on more than just what the probabilities of A and B are. This is not a major surprise. Because for conditional probabilities, we want to know how do A and B live together and whatnot. If you think of like the Venn diagrams, you can have your universe of discourse omega here. Here is maybe B, and here's A, coming in. And over here, that will be the probability of A given B. And essentially what we're doing when we do conditional probabilities is we change our perspective. And rather than looking at the entire space omega, we restrict ourselves to B, so we have to renormalize so that B now has essentially probability 1. I will risk this, my cultural references don't work. Anybody ever see The Mask of Zorro? So at one point somebody wants to avenge their brother who was killed. And Zorro is training the next generation of Zorro. I'm going to get my vengeance. And Zorro draws a circle around him and says, until I say otherwise, there is nothing outside the circle. No, there is that man and I'm going to kill him. No, this circle is your world. Until I say otherwise, this circle is your world. That's what we're doing here. When we're doing conditional probability, we are adjusting things. Now that we know B has happened, we can ignore all the things where B can't occur. And we assign 0 probability to that. So we're updating our probabilities. So that's how I want you to be viewing these conditional probabilities. And so the formula is the probability of A given B. Well, it makes sense that we should have a probability of B in the denominator. And the numerator is the probability of A intersect B. That's the probability that A and B both happen. So the probability that A and B both happen, this is A intersects B, and then I divide by B. As a special case, you could take B equals omega, the entire space. What's the probability of omega? 1. And then this reduces to just the probability of A. Reduces to the probability of A. So it's always nice when things reduce to things we've already seen. If we take the special case where B is just everything, then telling you that B happens is no information. We're basically just saying, yes, we are discussing probabilities. This becomes useful when you start looking at situations where the probability that B happens is not 1. And that by telling you that B happens, we now have some information. All right, so we've talked about some useful extreme cases to look at. There's a lot of different problems you can do. I will mention for later that this is highly suggestive of writing probability of A intersect B is the probability of A given B times the probability of B. And in fact, one thing that's nice about this formula is you don't have to worry now about what happens if the probability of B is 0. Well, if the probability of B is 0, what's the probability of A intersect B? 0. So we would have 0 over 0. This is undefined. Good. It's nice to have an undefined in a situation like this. It's not going to be that useful. The whole idea of these conditional probabilities is we can often use these to calculate the probabilities of events like A intersect B if we can calculate these constituents easily. So it all comes down to which calculation is the easiest one for you to do. If you think back to maybe calculus and some of the integrals you've had to do, sometimes if you write the integral in a certain form, it's easier to evaluate than another. And that's what we want to do, is we want to push events to a situation where we can evaluate them without too much trouble. So the example I'll do from the book is the one on fishing. Let's focus. So I think it's a 35% chance of a trout, no, 40% chance you catch a trout, 25% chance of bass, and a 35% chance nothing. So you go fishing for a day, and you either fish until the day ends, or as soon as you catch a fish, you stop and go home. And I tell you, 35% of the time, you get nothing. 40% of the time, you catch a trout. 25% of the time, you catch a bass. What's the probability you caught a trout? 40%. What's the probability you caught a trout, given that you caught a fish? So don't answer the question exactly. Give me some information about what the answer looks like. I want to know the probability you caught a trout, given that you caught a fish. What can you tell me? It's greater than 40%. So one way to solve this problem is the tree method. Is you start off with saying, let's have a huge number of days, and let's just have the probability flow down. I'm going to start with 1,000. I don't need to do that. I look at all these numbers and I say, what's a nice multiple? And so if I now look, 350 times, I have nothing. 400 times, I have a trout. And then 250 times, I have a bass. And again, I don't need to do 1,000. What number could I have done? 100. Could I have done something less? Yes.
I think you just do 1 and then like.
Well, you could do 1, but then you would have fractions. And I don't want to talk about a fraction. I like having nice whole numbers. It's the number theorist in me. Instead of using 1,000, I could have used 100. What else could I have used? 20. I don't want to deal with that. I don't want to spend time dealing with multiples of 20. Let me just overestimate and choose a number where I know things will be fine. So what fraction of the time do we catch something? So it'd be 650 times catch something. And so if we want to calculate the probability we catch a trout, given we got something, can we calculate that? Yeah, what would that be? Yeah, 400 over 650. So we can calculate a lot of these probabilities very easily. Later this semester, we might talk about some very interesting paradoxes. So a bad baseball statistic that is still used a lot is batting average. So it's essentially how many times do you safely hit per how many times you're at the plate. But there's a whole slew of what counts as a plate appearance and whatnot. I don't want to go into that. Let's just say how many times you hit the ball divided by how many times you're out. There's a situation where there are two players, David Justice and Derek Jeter. In each year, Derek Jeter had a lower batting average than David Justice. But over the 2 years, he had a better batting average. There are similar ones in looking at applications to people in graduate school where it looks like certain departments are discriminating and they're not. And it's a very interesting way of how you view numbers. And I will send you some stuff to look at about these paradoxes and how it is possible to be misled. You would think, well, if David Justice had a better batting average in each year, shouldn't he have had the better batting average total? What if he just barely wins in 1 year but has very few at-bats? And then wins by a tremendous amount 1 year and has a very large number of at-bats. And that was a lower. And in the year where he has a huge number of at-bats, maybe Derek Jeter has very few at-bats, so it doesn't weight that heavily. And so if you play games like this, you can actually be losing percentage-wise each year, but still win overall. So there's a lot of fun games you can play with manipulating statistics. All right, so what we want to do now is we want to talk about fun applications when the probability of B is not 0. We've actually seen a little bit of this when we've done the basketball game, in terms of trying to break down the probability that Bird wins. And we've secretly been doing what's called a partition. We've been splitting the outcome space into disjoint possibilities. And so one of the whole goals of these conditional probabilities is to get us to the point where we can calculate probabilities of complicated events by doing a lot of simple calculations. And depending on which way things go, one is easier than the other. So the first thing we'll do is Bayes' rule. So we said the probability of A intersect B was the probability of A given B times the probability of B. And now we're going to play one of my favorite games. It's called Cyclic Permutation of the alphabet. Okay? If I flip the order of A and B, does it really change anything? So this is the same as the probability of B intersect A would be the probability of B given A times the probability of A. But what is the probability of A intersect B relative to the probability of B intersect A? They're the same. So if these are the same, these must be the same. And so I'll just write it the same way I did over before. So the probability of A intersect B, which way do I want to write it? Okay. So the probability of A given B is the same as the probability of B given A times the probability of A divided by the probability of B. Just divide both sides by the probability of B. So this is the first version of Bayes' rule. And if you want to find what's the probability that A happens given that B happens, sometimes it's easier to find the probability that B happens given A happens. And if you know that and the probability of A and the probability of B, then you can deduce this. And so there are some examples in the book that go through where you know all the stuff on one side. What if you start trying to calculate the probability of A intersect A given B and you don't know the probability of B given A? Well, then maybe try doing it the other way. And maybe you calculate this using that one. Okay, so there's a lot of different things you can do. There's a lot of similarities between these. The last thing I want to say before going on to the theory of partitions is we have talked a little bit about how you present material and how you present probabilities. So there's a little bit of an aside. Unfortunately, one of you is deathly ill, and there is a chance that one of you will be dying in the very near future. But don't worry. There's a special procedure that has a 95% success rate, 95% survival rate. How do you feel?
Well, if we all have to go through it, then that means like.
Only one of you, only one of you. Does 95% survival rate sound good?
Sounds amazing. Yeah.
Sounds amazing. Unfortunately, while one of you has this, somebody else has a different rare disease, and that one has a 5% fatality rate. How do you feel about the 5% fatality rate? 5% of the people with it die. Not so good. Which would you rather have? The disease with a 95% survival rate or the disease with a 5% fatality? You don't want either. Is there a difference between the two? No. But depending on how you present the material, boy, can you influence how people look at things. Right? People often like to focus on successful things, focusing on living, rather than calling attention to the fact that you may not be with us for Friday. Okay. To the best of my knowledge, this was a hypothetical problem. I do not have any advanced knowledge that any of you have a rare disease. But how you phrase things can make a tremendous difference in terms of how people pass the probabilities and then what they do with that information. And a lot of times, especially in the medical field, you have to be extremely careful what you tell people because you don't want people to stop taking the medication. All right, so partitions. So we're going to have a set of things bi, and we want 3 things to be true. And the first thing we want for the b's, I'm going to try to do them in the same order. All right, this is the technical one. At most, countably many. We never want to deal with uncountable number of sets. So when we did the Magic Johnson, Larry Bird, we had a countable number of opportunities. Bird wins on his first shot, second shot, third shot, fourth shot, and so on and so on and so on. So it was at most countable. The second one and the third one, you can go back and forth in terms of which one you want second and which one third. The second one, we want the union of the bi's to be the entire space. Well, if I'm trying to partition omega, then the union of the b's damn well better be all of omega. Otherwise, I'm not partitioning it. Otherwise, something is left. And then the last one is we want pairwise disjoint. I don't want the b's to have anything in common. So if you think of this as omega, maybe here's the different b's. Maybe b1, b2, b3, so that we have nothing in common. And we're just splitting the space like this. And the question is, are there ways to calculate the probability of an event in terms of simpler events? So let's start off with the probability of A is the same as the probability of A intersect B union B complement. Because what's B union B complement? If it's not 1, it's essentially 1. Its probability is 1.
It's omega.
It's omega, it's everything. So A intersect B union B complement is just A intersect omega, this is just A. I haven't really done anything. This is going to be the same as the probability of A intersect B plus the probability of A intersect B complement. So if you think, here's B complement, here's A. If I want the probability of A, it's the probability of things that are in A and B plus the probability of things that are in A and B complement. So this is a simple way to start calculating probabilities. Now, the probability of A intersect B is the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. So this is the first way to calculate the probability of A. If you want to think about it, the probability that Bird wins is the probability that Bird wins on his first basket, on his first shot, given that he So what do I want A and B to be? So I want probability A given B. All right, so the probability that Bird wins, given that he makes his first shot, times the probability he makes his first shot, plus the probability that Bird wins, given that he misses his first shot, times the probability he misses his first shot. And so this is a simple version of expanding things out. Unfortunately, for the Bird magic problem, there's more than just 2 options. Right? What else could happen? He could make it on his first shot, his second shot, his third shot. Well, now we just do the lather, rinse, repeat method of mathematics. Right? We would then split this one up. And you can keep playing these games, and what you'll get is the probability of A should be the sum of the probability of A intersect BI, where the BI are a partition. And essentially what we're doing is we're saying, look, if we have more than one possibility, here's B1, here's B2, here's B3 over here, what's the probability A happens? It's the probability that A happens and it's in B1 plus the probability that A happens and it's in B2 plus the probability that A happens and it's in B3. We're just breaking it up into all those pieces and then adding. I could then rewrite this as it's the sum of the probability of A given BI times the probability of BI. So a lot of times these calculations become very easy to do. You know, the calculation of A given BI, and often the probability of BI is easy. And if we can do all of these, we can then combine them upward and get the other one. As a rule of thumb, which would you rather do? One tremendously difficult, challenging problem, or a plethora of easy, simple calculations? A large number of easy, simple calculations. Which one would you rather do?
Bunch of easy ones.
Bunch of easy, especially if you have a computer to animate and you know, run all this stuff for you. It's much better to just do small, simple things and then piece them together. The whole idea of this theory of partitions is just piecing things together. Okay? Now, if we can't calculate these probabilities, then this is worthless. But in many situations, we are able to calculate these probabilities. And since we can calculate the probabilities, it's a good trade. Right. So we only have one last thing to do for today, and it's the inclusion-exclusion formula. How many of you have seen inclusion-exclusion? We will see later how valuable it can be. So, inclusion-exclusion. And I'll do it through an example. Let's say you have events A1, A2, ... AN. And you want to calculate the probability of A1 union A2 union AN. It turns out unions are terrible to work with. Intersections are much easier to calculate. With a union, I worry about it's got to be in either A1 or A2 or A3. It occurs somewhere. If something occurs in multiple A's, I have to be careful not to count it multiple times. So I claim that this is just the sum of the probability of each AI. Is that right? No. As a ridiculous extreme, imagine each AI is omega. Then this union is just omega, its probability is 1, and dear Lord, I can make this as large as I want. So always look at these extreme cases. So this clearly can't be the whole story. But what I'm doing is, let's say I have some number x. If x occurs, imagine these A's were disjoint. Is this true now if they're disjoint? Yes. So it's okay if they're disjoint. Now imagine, maybe disjointness is too much to ask, but maybe there's no x that is in more than 2 of them. So if there was an x that was in both A1 and A2, I've double counted it. If there was an x that was in A2 and A3, I've double counted it. So what do I have to subtract? So this would be I go from 1 to n. Subtract what? So I've double counted things that are in 2 of the A's. So I would have 1 less than equal to I less than j, it can't be the same set, less than equal to n of the probability of AI intersect AJ. This would be all the different things where something has occurred twice. And so if you think about it, if x has occurred in A1 and A2, then I counted twice over here, and I subtract once over here, the net counting is 1. What if something occurs in A1, A2, A3? I've now counted it 3 times here. I subtract once from A1, 2, once from A1, 3, and once from A2, 3. Oh crap, I'm not counting it at all. So what do I have to add back in? Yeah, plus 1 less equal to I less than j less than k less equal to n of the probability of AI intersect AJ intersect AK. But what if something is in 4 things? Then you subtract. And at this point you say, you know, I understand what the pattern is and I don't want to write it. And so this is the idea of inclusion-exclusion. What's nice is you can get over and under estimates frequently. a lot of times all of these probabilities will be the same. So the probability of A1 intersect A2 will be the same as the probability of A2 intersect A3 will be the same as the probability of AN minus 1 intersect AN. So it would just be how many ways can I choose two distinct indices from n times one of those probabilities. So in that case, it often simplifies to just n choose 1 probability of A1 plus n choose, minus n choose 2 the probability of A1 intersect A2 plus n choose 3 probability of A1 intersect A2 intersect A3 minus dot 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 dot. So frequently we're lucky enough to be in a situation like that. And then not surprisingly, this is going to be connected to the exponential function. If you think about the factorials that are beginning to come into play here. So there's a lot of stuff we're going to do. In the next class, we might look at what is the probability that at least one person is dealt all one suit. So you have 4 players, it's damn unlikely. So I want to calculate the probability that somebody has all their cards in one suit. So what I could do is, I have 4 players, A1, A2, A3, A4. What's the probability somebody has a one-suited hand? That's going to be a union. All right. I could just go for the sum of the probability that just one person, your specific person, has a one-suited hand. Then I would have to subtract off the probability that 2 people have a one-suited hand. Well, it's unlikely one person has all their cards in one suit. It is even more unlikely by a tremendous amount that 2 people. The amount of change of this is insignificant. The amount of change from the next term that 3 people, actually if 3 people have one-suited hands, what do you know? The fourth one does as well. So we have reached incredible unlikeliness very quickly. So if you try to do the calculation and you try to simulate it, odds are I don't think your computer will be strong enough to actually see the difference in probability by adding this term. This is going to so dwarf things. Imagine you're trying to measure the light intensity from the sun. And unfortunately, there's some asshole who has a rocket ship and they have a little flashlight and they're turning it on and they're between the sun and you, very close to the sun. Are you going to notice that? No, right? The sheer magnitude of the illumination from the sun is going to drown out that extra flashlight. If you wanted to calculate it, is it still there? Absolutely. For all practical purposes, however, you could ignore it with the calculation. This is one of the dangers when you're trying to prove things theoretically. If you were to do the simulations would support just that. And so you want to be very careful. How many of you have taken a stats class where you do hypothesis testing? Okay, I'm not going to go into that in this class, but you're very careful about what you say when you do hypothesis testing. Right? What do you never say?
Causes.
You never say with like causes. You never say we've proven that this is happening.
Oh, we never accept.
Right. So there's always there's a real careful language that is done because the data can't prove. The data can often disprove. Imagine you believe that a coin is always going to land heads, and you toss it 1,000 times and you get 995 heads. You've disproved that it's always heads. You can do things like that. But if you believe that there's a 5% chance of heads or 0.5% chance, you'll never be able to prove or disprove that. All right, so this is a good place to stop. We have 1 minute.